Maybe like this. Okay. So, hi everyone, I'm Berkay. I'm from TU Delft, and today I'll be presenting you our work on model-guided fuzzing of distributed systems. So, finding concurrency bugs in distributed systems is notoriously difficult. They're highly concurrent, non-deterministic, and prone to subtle bugs that only often surface in production. Random testing can help, but it usually misses the deeper issues. Promising technique is coverage-guided fuzzing. Does it work like this? Yeah? If it works like this. Yes? Okay. What was that? Yes. So random testing can help, but it usually misses the deeper issues. The promising technique is coverage-guided fuzzing, which is proven effective for sequential programs. But applying fuzzing to distributed systems introduces unique challenges. In particular, existing coverage metrics don't translate well. So we end up with the question, what is a good notion for coverage? To answer this, we thought formal verification methods exist for verifying distributed systems. So is there any way for us to leverage them to guide fuzzing, for them to guide fuzzing? So our idea is to power fuzzing with abstract formal models. In this case, TLA plus models, which are often available from protocol design. The key benefit is abstract model keeps essential information, but at the same time allows us to abstract away implementation level details. So now, instead of measuring something like code coverage, we treat the model states as our notion of coverage. Each time the system explores a new state in the model, that's feedback to the fuzzer. In other words, the model becomes a guide. It steers fuzzing towards unexplored and interesting behaviors. So then we should also ask the question to ourselves, why existing coverage notions are unsuitable for distributed systems. So let's illustrate this specifically on code coverage, why it is unsuitable, with a simple example. We have three processes, an app master, a worker, and a terminator. The app master coordinates requests, the worker executes them, and the terminator handles cleanup. When the app master receives a request, it sends two concurrent messages, one to execute and one to terminate. The worker runs this task on execute, and notice here that the developer here forgot to put a null checker on its buffer. Meanwhile, the terminator receives the message and sends a flash to the worker to clean up. This is the intended behavior. Now let's consider what happens if the network conditions change the order of the events. The setup is exactly the same, but this time the execute message is delayed and the cleanup happens first. The terminator flushes the worker before its task is executed, and when the execute finally arrives, the worker tries to use its buffer, which is now null, and this results in a crash. What's important here is that both executions cover the same lines of code, but lead to very different outcomes. The bug here lies not in the code coverage, but in the ordering of the events. So unlike code coverage, model states capture the overall behavior of the system, ordering of the events, message deliveries, process interactions, not just which lines of code were actually executed. This means that two runs that execute the same code, but in different orders, map to different model states. As a result, model state coverage captures the effects of concurrency between executions, making it far more effective for testing distributed systems. So, code coverage is out. Another idea is to use Mazurkiewicz traces. They're useful for distinguishing schedules syntactically and already account for concurrency as they consider the orderings of dependent events. But in practice, they're too fine-grained. They consider many orderings that ultimately lead to the same overall system behavior. So here's an illustration why traces are too fine-grained. In this state diagram, we can see how different event orderings lead to very different outcomes. But even for this tiny example, this diagram only represents a small fraction of all possible states. In real distributed systems, the state space grows exponentially with the number of nodes, messages, and other variables. On top of that, many systems include an additional setup phase, like we have in our example here. This phase often creates a bottleneck in exploration, and we don't want to waste our exploration budget navigating through it repeatedly. If we think of the circles as the system states and traces as the paths between them, we can see that many different traces lead to converge on the same state, making them unsuitable for effective guidance. So to go back to the key question, a good coverage notion should also guide us effectively through these enormous spaces. What you really need is a notion of coverage that captures the semantics of the system, not just syntactical differences in traces, but meaningful differences in its states. By using model states as our coverage metric, we capture these semantics directly. Each model state represents a distinct global configuration of the system, its processes, messages, and interactions. Trace-based coverage, on the other hand, still distinguishes many schedules that ultimately lead to the same behavior. Model state coverage abstracts away the redundancies and focuses only on what's truly different. So traces are out of the picture, as it both captures the concurrency of the system and distinguishes between the semantics. Abstract formal models provide the balance that we're looking for. So before I explain how we extend fuzzing with models, let's quickly review the basic fuzzing loop. In a typical coverage guided fuzzer, we start with a system S and initial set of test cases T0. We pick one test case, run it on the system, then collect some form of coverage notion. So there's something simple like line coverage, for instance. If this execution hits new lines, we mutate this test case and add this mutated version back to our pool. If it doesn't explore anything new, we discard it, and the loop continues. We extend the base coverage guided fuzzer with the additional components seen here in orange. This is our fuzzer, model fuzz. Instead of raw inputs, we provide seeded schedules to the system on the test, and we execute them with a control scheduler. This matters because in distributed systems, the same input can lead to very different outcomes depending on the ordering of the events, as they're highly non-deterministic. The control scheduler is there to enforce that ordering. Next, we map the events that we collect during the execution into model actions and run them in the model checker. We track which states the model reaches and then feed that information back to the fuzzer. If we uncover new states in this process, we mutate the schedule and add it back to the pool. So we end up, at the end, we end up with a loop where the fuzzer generates schedules, the system executes them, and the model provides feedback to the fuzzer. The feedback loop continues to drive the exploration towards previously unexplored model states, allowing model fuzz to uncover unique and interesting system behaviors. We evaluated our fuzzer on several distributed systems, namely two-phase commit and two production implementations of Raft, Etcd and RedisRaft. For baselines, we compared them against random testing, trace coverage, and line coverage, and bonus max RL, a reinforcement learning-based approach. Across all of these, we measure two things: how much coverage each method achieves, and how effective are they at finding bugs. When we look at the coverage, model fuzz consistently outperforms random testing, as well as line and trace coverage. Compared to bonus max RL, model fuzz achieves overall comparable performance with bonus max RL, but it outperforms us, especially on the Etcd benchmark. But when we look at the overall results, we demonstrate that using abstract model coverage is an effective way to guide fuzzing in distributed systems compared to other coverage baselines. When we turn to bug finding, model fuzz not only discovers bugs at comparable speeds to the other approaches, but also uncover bugs that they completely miss. So you don't need to actually read the table, but for example, in RedisRaft, we found 13 bugs in total, and 11 of them are new bugs. Specifically, model fuzz was able to detect almost all of them. Importantly, 3 of those bugs could only be found by model fuzz and could not be detected by any other method within the test budget. We also discovered a new bug in Etcd-raft, again only found by model fuzz. So with these results, we show that model-guided fuzzing isn't just about increasing coverage. It also directly translates into uncovering real impactful bugs in production-grade systems. So moving on from our results, let's look at where model fuzz fits within the broader space of related work. First, there are randomized approaches like Jepsen, which uses random fault injection to uncover consistency violations, and PCT-CP, which explores the state space with probabilistic guarantees. Then we have some systematic testing methods, such as PSIM and debug. Next, we move on to the learning-based and model-assisted approaches. For instance, QL and bonus max RL use reinforcement learning to guide their exploration. On the model-assisted side, Mocket directly generates traces from the model. Trace validation checks executions against model specifications, and must integrates validation checks. must adds model checking for runtime verification within systems. Mallory and model fuzz creates a middle ground here. So Mallory doesn't directly use a model, but while Mallory allows the usage of TLA plus specifications, where they leverage the specifications to annotate interesting events within the source code. Whereas with model fuzz, we more explicitly use them for coverage feedback. Now, so let's look at one of the most closely related works in this space, as we've shown, which is Mallory, a Jepsen-based reinforcement learning-driven fuzzer for fault injection that guides the exploration through user-annotated points of interest. So we compare model fuzz and Mallory on our shared benchmark, RedisRaft. The first key difference lies in how they learn from executions. Model fuzz runs many short tests, while Mallory learns through one single long execution. Because Mallory's long execution produces event traces too large to model check directly, we modified its implementation to collect abstract state information during runtime through logging. We then reconstructed the sequence of system states using the same model state definition as we use in model fuzz. So on top, we show the abstract model state coverage of Mallory and model fuzz under the same abstractions. Both perform similarly with model fuzz, achieving slightly higher coverage. In our model, we also include a set of active processes, capturing crashes and restarts, as part of the abstract state definitions that we have in our TLA plus model. Since Mallory's logs lack this information, we also provide a comparison on the bottom, excluding these details, where coverage remains similar. On the bug finding side, model fuzz replicated 2 bugs previously found by Mallory, and we also have 11 new bugs that we found. So in general, overall, they have complementary bug finding capabilities. So finally, we also have our limitations. It mainly consists of having a balance within the model. So if the model is too abstract, it will miss important behaviors, such as like process crashes or restart. But if it's too detailed, it ends up distinguishing between similar system behaviors. So the real challenge here is finding a balance within the model. So to conclude, going back to our initial slide, we had some questions. Now we answer them with model fuzz, a fuzzing approach that leverages abstract formal models and uses them to guide exploration in distributed systems. We showed that it improves coverage, consistently finds bugs, and even uncovers previously unknown bugs in real raft implementations. The key takeaway here is that abstract models aren't just valuable at design time, but they can also serve as powerful guides for continuous testing of distributed systems. Thank you.
Thank you for the talk. We have time for about 1 or 2 questions. Yeah.
Thank you. Great talk. So I have one question according to the models you're using. So did you implement them? And when you have the model, how easy it is for you to map the model state to the implementation state? Say like I don't really know raft. Like how long does it really take for me to map those 2 parts?
So the first part of the question, the models already exist. So there's a huge repository of like existing protocol, like TLA plus specifications. We focused on that. And the mapping is actually the mapping of events to the model actions are actually quite simple. So let me give you an example on raft. Like the model itself uses like elect a leader. So you can just, whenever you elect a leader, you can use it as an event, or it uses messages as actions. So you can just map them directly. So implementations are also driven by the models themselves.
Thanks.